Yeah, thank you everyone for joining me today. Appreciate you taking the time to learn more about 475 and foam-free, smoke-tight, and resilient building enclosures. So I'll just go ahead and dive right in. If anybody does want to jump in and ask questions as we go, I'm more than happy to do that. I'll also make time for you to ask questions as well. So I will just get going here. Oops. All right, perfect. So just brief introduction about me. I actually grew up in Healdsburg, California. So I know a number of you guys are in the East Bay and probably familiar with Sonoma County and Healdsburg. So that's where I'm from. My dad was a builder there for 35 years as a GC. And a little bit about my background. I worked for Greenpeace for a little while, waving people down on the streets, asking for donations. I worked for a lighting rebate program in the Sierra Nevada mountains, helping commercial businesses get LED lighting. Um, I've worked doing energy modeling for the state of California, as well as for an engineering consulting firm in Portland to assess energy efficiency upgrades. And I've worked on regional energy efficiency studies and indoor air quality studies in the Pacific Northwest. I've been with 475 since 2018, and I serve 8 states in the West, and I do live in Oregon. So same time zone as you all, even though 475 is based in Brooklyn. So what is a high performance building, right? This is what we're asking today. And these are a few elements of a high performance building. You know, energy efficiency is, I think, one we're all really familiar with. Having a very comfortable home. We're talking a lot these days about a smoke tight home and a healthy home. I also really like talking about a resilient and safe home. You know, I know in California, if it's too hot, PG&E will cut your power. And if your home is not insulated very well, that home could get really, really hot during that heat wave and create unsafe conditions for the occupants. So by investing in the envelope, we can help protect the occupants of the building. So how do we get there? How do we make this high performance building, right? Well, typically we're looking at minimizing thermal bridging. We're looking at high levels of insulation, really great, typically triple pane windows, an air and smoke tight envelope. And then since it's air and smoke tight, we want to have a filtered fresh air system, typically an HRV, to provide the ventilation to the space. So today, in terms of the components of our high performance building and how we get there, I'm mostly just going to be talking about the enclosure today. You know, there's many other components of a building that make it high performance. But again, today, it's just on the enclosure. And today it is the foam-free presentation, right? So we're going to knock foam a little bit today. So, you know, as you can see, once it's installed, if you want to do any type of retrofit or change to the wall or roof, it's going to be a little bit challenging since that material can be adhered to the studs. The material can set up improperly. That photo in the middle is actually from a project in Truckee, California during the construction phase. So yeah, poor installation can be an issue for many products when we're trying to achieve air tightness. But foam, in terms of performance, it does shrink over time. It's not dimensionally stable. And as framing members expand and contract due to temperature and humidity changes, that foam insulation doesn't move. So it can actually crack away from framing members long term because those framing members are expanding and contracting. Foam also has a pretty high level of embodied energy or embodied carbon. You know, we've done really well at getting our operational emissions down. And so the new focus for a lot of firms is to reduce the amount of embodied carbon or the amount of CO2 that's released by just putting the building together. Foam is also made with not the most wonderful chemicals available on the market. And if it does catch fire, it can become a fire accelerant and create some pretty unsafe fire conditions. So today, my hope is to inspire you to build better assemblies, ones that are more robust, resilient, sustainable, higher performing, higher quality, and healthier. So back to those control layers, right? And this high performance home, I'm going to be talking about water, air, vapor, and thermal control today with respect to our high performance building. Because if we don't get the water protection right, we can destroy our building very, very quickly, right? I also like to touch on the fact that if you do have some water intrusion into your building, it can create indoor air quality issues, right? If you get some mold and rot in your house, those mold spores can enter your home and compromise your indoor air. We like to talk about rain screens. So rain screens are basically a gap that's created between your exterior siding on the wall and the WRB, right? So that gap can be a variety of depths. It can be anywhere from a 1/16 of an inch to, over an inch deep. And the benefit of having that gap is if you get some rainwater that gets behind your siding, it has an opportunity for that water to drain out of the building or out of the wall. In addition to that, if you're over about a 1/2 inch of depth, um, you can actually have air movement through that rain screen cavity. And when you have air movement through the rain screen cavity, that helps dry that wall assembly out much more quickly. And with respect to our high performance buildings, we'll get more into this in the vapor control section, but essentially we have to be hyper vigilant protecting our buildings from water and water intrusion because our over insulated buildings take longer to dry out. If you don't have enough space for, say, a 1/2 inch or a 3/4 inch batten, something like that for your rain screen, there are really great mesh products available on the market. This specific mesh product, which is 10 millimeters deep, does meet the code in that marine climate, which you can see is just to the left of that dark black line. So if you have any projects in coastal California, you're looking at stucco, this can be a product that can be used, or I should say a 3D mesh product can be used for that. And then just a nod to peel and stick products, right? There's a number of house wrap products that you can use, WRBs, water resistant barriers. And if you use a product that has an adhesive on the backside, basically a giant roll of tape that can stick to the side of the building, you have better sealing around penetrations and fasteners. And you have more durable protection during the construction phase against that water intrusion. So you all have the opportunity to spec out products, right? Or do design features that help make the home more resilient with respect to moisture intrusion, right? You can use like a metal siding, you can have deeper overhangs. There's obviously a lot you're thinking about in terms of protecting the building from fire as well and protecting it in that way. But essentially, there's different WRBs on the market, and they use different technologies. So typical house wraps on the market that you'll find at any lumber yard, these are microporous membranes. So that picture on the bottom that I'm circling with my mouse, these microporous membranes have tiny perforations or holes in the material, and this is how they become vapor open, right? The material itself isn't vapor open. So as water vapor on the inside of the building tries to migrate out, we want to allow that water vapor to escape. We don't want to trap it in our walls and create moisture issues. So all house wraps are designed to be vapor open, right? Microporous membranes, they don't have any active pores in the material, so they actually have to perforate the material to allow air to move that water vapor through the material. The problem with putting holes in your water and air control layer, right, is the fact that you have holes in it. There are other products on the market that are available, ones that are monolithic. These actively transport water vapor molecules at the molecular level, so they don't have to be perforated to be vapor open. So these products are typically about 100 times as airtight as typical house wraps on the market. They also resist over a 33-foot water column of moisture with respect to water protection. So the products that you select for your house wraps have a big impact on water, air, and vapor control. Any questions on the water control section? Alrighty, it's pretty straightforward. So I'll keep going. So the next section that we're going to talk about here in terms of our robust enclosure, right, is air control. And air control has a number of benefits. So first one is we do have outdoor air pollution, right? In California over this decade, we had increasing air pollution. I think you all have been spared over the last 5 years or so compared to that 2020 year. But essentially, outdoor air pollution can cause issues with our health, right? So if we make our buildings more airtight, we prevent outdoor air pollution from coming into our homes and make the spaces healthier and more comfortable to live in. What's great about measuring air tightness is it's very straightforward. There's a blower door test that you can use to either pull air out of the building or force air in, and we can understand how air leaky that building is. and we can also find out where those leaks may be. So with respect to energy efficiency, air control has a big impact. So this little picture here on the bottom right, this is the Darmstadt Passive House in Germany, is the first passive house project ever designed, certified, and built. And this building already has, triple pane windows. They've minimized thermal bridging, high levels of insulation, all those great things for a high performance building. So what we did is we decided to model just the air tightness of that building, and we wanted to see what the associated kBTUs per square foot per year of heating demand would be based on that air tightness. So this ACH 50 value, this is a value of how airtight the home is. If the value is higher, that means the home is more air leaky. If the value is lower, that means our building's more airtight. So you can see here that the amount of heating energy we're using as the building gets more and more airtight goes down. And what you can see right here is this is a 0.6 ACH 50, which is what's required for the residential passive house standard. And you can see that the heating demand is at about 4.75 kBTUs per square foot per year of heating demand. And that's where 475's name comes from, if you were curious. So what does this mean, right? More energy efficient building. This means smaller mechanical systems, certainly going to save on operational costs during the life of the building, but it may also save costs up front. Another big impact of air control is actually moisture control. And so once we've kept the rainwater off the building, the next thing we want to be able to control is air, because air can transport a lot of water into our wall assemblies. So this is a Building Science Corporation study in Chicago, granted a much colder climate, but first they looked at one 4x8 sheet of gypsum board over the course of one winter, and they wanted to see how much water vapor diffused through that 4x8 sheet of gypsum board. And they found that about 2/3 of a quart of water diffused through that sheet of gypsum board. So not a whole lot of water getting into that wall assembly via vapor diffusion. But then what they did is they looked at the same time period and they cut a 1 inch by 1 inch square hole in that sheet of gypsum board. And they found that up to 95 quarts of air transported moisture moved into that wall assembly. So, again, with our high performance buildings, these are going to be over insulated. And if they get wet, it takes them a lot longer to dry out. So we want to be more vigilant about air control in order to keep our buildings dry and keep them free of mold and rot. Encapsulation of the insulation also provides additional benefits, right? So if we make our insulation airtight, we're going to allow that insulation to perform to its rated R value. If any of you have been outside on a cold, windy day wearing a fleece, you'll know that the wind cuts right through that fleece and it doesn't keep you warm. But as soon as you throw a windbreaker on there, that fleece is keeping you nice and warm. Because after all, insulation does not achieve its R value based on the material itself. Like it's not the fiberglass that creates the R value. It's actually the tiny pockets of trapped air within that insulation that create the insulative value. So if you have air moving through your insulation, it really, really degrades performance. And so again, just a nod to peel and stick products, right? These are going to reduce air movement between the sheathing and the WRB because it's actually adhered to it. They naturally seal up the sheathing butt joints. It's not going to get blown off the building in the construction phase. And if you are using exterior, continuous insulation on the outside of the walls, you're going to have many more fastener penetrations going through this air control layer. So a peel and stick is going to better seal up those penetrations in the short term and the long term. So touching back on foam insulation again, right? So foam is touted as an air control material, but as we know, it can shrink over time. It's not dimensionally stable, so the foam can actually shrink away from those framing members, creating air leaks. It can obviously be installed poorly to the point where the material isn't even adhered to the studs in the first place. And then again, the framing members are going to expand and contract due to temperature and humidity changes over time. And that foam's not going to move with that material. So the foam can actually crack away from the material very easily. This Assyri Designs, if you're not familiar with Assyri Designs, they're great. They're out of Portland. And they have some really great videos. One of them here that describes what I'm talking about very clearly. So with respect to your air control layer, right, we want to use really great robust materials that are durable and long lasting. We want to simplify the details because the air control layer could also be the water control layer. And there's someone on site who has to detail the air control layer properly. And then, sealing up penetrations to windows, pipes, and wires, that's straightforward. And then we also want to make sure that we can protect this air control layer long term and be able to repair it if it gets damaged during the construction phase. So the connections of your air control layer, there are these different connections that happen, right? Walls to windows, things like that. Typically, windows are sealed with a backer rod and caulk, but that caulk can dry out and embrittle over time. There are new products on the market, products that use a solid acrylic adhesive that have been tested for 100 years of adhesion, and they're able to move with the building over time. So long-term air barrier strategy, it's best to use products that are going to last the life of the building. Just a nod to windows here and indoor air quality. So, as we know, we've had some smoke events, and typically triple pane high performance windows are gasketed in a way that make them really airtight. Typical window manufacturers aren't necessarily designing their windows to be airtight. And if you do have outdoor air pollution, this is a pathway for the pollution to get in, even if our windows are closed, because many windows are not designed to be airtight themselves. So with respect to this critical air control layer, right, that's giving us energy efficiency, health, keeping moisture out of our walls, we do get additional benefits by putting that air control layer on the interior side of the stud bay. And your air control layer can be your WRB on the outside of the wall. It can be taped sheathing. Oftentimes it's the interior drywall. But you can also place this air control layer on the inboard of the studs. And so by doing this, you get additional benefits against potential condensation risk. So when we're heating our homes in the wintertime, it's cold outside, you could have warm air sneak into a wall cavity, hit a cold surface and condense moisture. It's exactly the same reason why on a hot day outside with a cold drink that the outside of the drink gets wet, right? We have warm air that hits the cold glass, the air cools down and it leaves behind moisture on that glass. That glass is the condensing surface. So if we keep our warm, humid air away from that cold surface, we greatly reduce that likelihood of condensation because that warm, humid air can't reach that cold surface. So if you are using this approach where you're using an interior air control layer, which helps better protect against condensation risk, mold and rot, things like that, using a service cavity can be really beneficial. This provides a chaseway for electrical outlets, electrical wiring, and it also puts the air control layer away from the occupants, right? It's a little bit further away, so when the occupants are punching the drywall or punching nails through it, it's staying away from our critical air control layer. It's also a great benefit for retrofit projects too. If you're only opening up the inside of the building and you want to air seal it, this can be a great way to do it. And it's also important to note that even though the service cavity really helps the material, it's not required to use an interior air control layer. And so now that we've gotten the building airtight, we want to ventilate it right. And we can do that either with a centralized ventilation system. We can do it with a decentralized ventilation system. And what these systems do, right, is the best options have heat recovery. Heat recovery allows you to bring in that outdoor air and recover the heat so that it makes the building really energy efficient. But essentially, these ventilation systems, right, they're bringing in outdoor air, they're filtering that outdoor air, they're removing any pollutants in the outdoor air in the filter before that air gets inside. And then they're also removing stale air from the interior, which there can be many, many pollutants inside our homes, and being able to remove that stale air is critical for health and wellness. All right, any questions on the air control section? Yep, Kirsten, looks like you have a question.
Yeah, can you hear me?
I can.
Oh, okay. Um, can you go back to the air control layer? I know it's put, yeah. And I don't know if it was, yeah,
I
this
can
one
go
or maybe
back a little further
this one.
here.
Yeah, so there, yeah, so here it looks to me that the air control is right on the interior of the sheathing. Is that right? Or
It's actually on the interior of the studs and on the
of the studs?
interior of
Okay.
the roof rafters.
Oh,
Yeah.
so you're showing an additional what you call it a service cavity in front. That's what you're
Hmm.
creating here, right? With the horizontal slats.
Yeah. Hmm.
Okay.
And again, that service cavity, service chase, it's not required when you're using this strategy, but it is helpful for minimizing the amount of penetrations that go through that air control layer and sort of protecting it from the occupants long term.
Okay. And so the air control layer, what you call air control layer, is the membrane. Is that correct?
That's correct.
No.
Yeah, that is correct. Yeah. The air control layer that I'm describing would be the membrane that you see in the picture.
Okay. Thank you.
Yeah, absolutely. And I can send out a PDF of the slides as well. I see you asked that question. So yeah, I'm happy to send that to the AIA East Bay folks. Great. Any other questions I can answer before we move on to the vapor control section? All right, I'll keep going. Perfect. So I alluded to this earlier, but essentially our older, poorly insulated buildings, right? They have large heating systems that can keep the occupants comfortable, right? And one benefit of this really large heating system and a lack of insulation and airtightness in our walls is we actually have a lot of heat energy moving through that wall. So if you have a window leak or you have really humid conditions inside the home for whatever reason created by the occupants that gets into the walls, these walls can actually dry out very easily. And you can see that here on that image on the left-hand side, basically where this is a wintertime condition and they're heating the inside of the building. It's cold outside and we have lots of heat moving out through the building. So now when we pivot over to the right-hand side of the picture, right, this is our highly insulated assembly. We've got very small heating systems on the inside of the buildings, keeping the occupants comfortable, reducing energy consumption, keeping them safe in case there was a power outage, things like that. But now if we have a window leak, we don't have as much drying potential. So by investing in the envelope and making our buildings more high performance, we are increasing moisture risk because you have less R value, or excuse me, you have more R value, you have a more higher resistance to heat moving through that wall assembly. So we want to allow our buildings to dry out via vapor diffusion. So just a little overview of vapor pressure and which direction vapor drive typically is. In the wintertime, when we're heating our homes, the indoor air is a higher temperature and compared to the outdoor air. And vapor moves from high concentrations to low concentrations. So your indoor air, since it's higher temperature, it typically has a higher vapor pressure, even if it's cold and wet outside. So water vapor tends to want to drive outward during the winter. So basically what's best if we want to keep vapor out of our wall assemblies is to have on this blue line some type of vapor control layer, a vapor retarder. Again, on the outside of the wall, let's say you had a window leak, something like that. We do want that wall to be able to dry outwards. So we want to have vapor open insulation, sheathing, things like that. If we've got a rain screen too, that's great. And that allows the any moisture that is in the wall already to dry to the exterior side. Now in the summertime, that condition can be reversed. And the way that it can be reversed, right, is we're cooling on the inside of the building. We're nice and cool inside. It might be pretty hot outside. And let's say that we had a window leak and we got some water and we saturated our insulation, our sheathing, our exterior insulation. Now you have western sun baking the outside of the wall and it's driving that water vapor back into the building. This is when we want that blue line to not be vapor retarding. We want it to be vapor variable, open up, have a higher perm rating to allow that wall to dry out towards the interior side. So again, we're minimizing the amount of water vapor and moisture that can get into our walls in the first place, but we're also allowing them to dry. So when we put a vapor closed foam-based insulation on the outside of our buildings, this is going to help with energy efficiency. The home will probably be more comfortable in terms of temperature and things like that. But if you do get a window leak or you have water sort of move between that foam insulation and the WRB and it starts to saturate the wall, this building can only dry out inwards during the summertime when you're air conditioning the inside of the building. Because essentially in the wintertime, when you're heating your building and that water vapor naturally wants to push out through that foam insulation, it's just gonna stay there. It can't move through that insulation. So this is a more energy efficient, high performance home, but it's reducing our drying potential, which is increasing risk. So this was a Building Science Corporation study in Minneapolis, Minnesota. Again, much colder climate than the East Bay. But essentially it looked at the interior face of the exterior sheathing, and it looked at the relative humidity there. So again, they're looking at the relative humidity at the interior face of the exterior sheathing. And they're looking at that over the course of about a year, winter, then summer. And they're looking at 4 different wall assemblies. So what we can see is with the standard 2x4 and 2x6 construction, the humidity goes up in the wintertime a bit, humidity goes down in the summertime when there's inward drying. And this is an indication that water vapor is moving towards the outside of the wall. With the 2 blue lines with the walls with 1-inch XPS and 4-inch XPS, we actually see that that vapor drive wants to get out in the wintertime, right? And it's not able to. So the humidity at that interior face of that exterior sheathing is building up. And what you can see here is this line at 80%, right? Mold can start to grow at 80% relative humidity. So, does this mean mold is growing in this wall? It's anybody's guess. But it is an indication that the conditions exist, wood sheathing and humidity for mold to be able to grow. And you can actually see here that we reach 100% humidity during a few times of the year, which is dew point, right? That's when the moisture actually comes out of the air. So, the question for you all is, does foam make our buildings more or less tolerant of moisture? Hopefully I'm explaining this all well and you feel like foam makes our buildings less resilient with respect to moisture management. So we like to recommend vapor open exterior sheathing that allows our buildings again to dry outwards. In colder climates where you're putting a lot of insulation on the building, you can put your structural sheathing on the interior side of the wall and put all your insulation on the outside, which allows for really great drying potential. So going back to this blue line here, right? This is our interior vapor control or vapor retarder. And we can use a number of materials for this interior vapor control layer. As you saw in this image back here, this project is using taped OSB for the vapor control. This project here is using a membrane. So these different products have different levels of permeance and they have a differing vapor variable qualities. So that OSB, it's pretty vapor closed, right around 2 perms. It's not really opening up more than that. It's not really closing more than that. The other vapor control membrane that you saw in the image in the last slide, that is a smart vapor variable membrane. And as you can see, it can adjust its perm rating in a much larger way. And that's because these products are designed to manage water vapor in an optimal way, and they are humidity dependent vapor control products. So again, we're looking at, winter time conditions over here on the left, summertime conditions over here on the right. This orange line is our vapor control layer, and the interior of the building would be below this orange line. So this is maybe looking more at a roof assembly. So we have the path here of vapor drive, right? It's warm inside, cold outside. That water vapor is going to drive towards the cold side of the wall. But as you can see, during the wintertime, this material can actually be all the way down to 0.13 perms, which is nearly a class 1 vapor retarder. So it's preventing humidity from entering our insulation. It's keeping that humidity in the house, out of our insulation and out of our framing, which is helping this stay free of mold and rot. Again, let's pivot over here in the summertime. Let's say that you had some type of leak. We've got some moisture in this insulation already. We're air conditioning on the inside. You've got hot summer sun on the outside, baking the outside of the wall. Now we have vapor that's driving, excuse me, into the building, represented by this line here. And now this humidity dependent vapor retarder can actually open up all the way to 13 perms and allow for inward drying, letting our buildings dry out, and reducing the chances and likelihood of mold and rot. So this is the vapor curve for one of these products that exists on the market. And so what you can see here is permeance on the left on the y-axis, and we have relative humidity on the horizontal x-axis. So again, these are humidity-dependent vapor control layers. So you guys can either speak up or put this in the chat, but what humidity do you think your home is typically at in the wintertime? Your indoor air, you're in your house, you're heating the home, it's cold outside. What relative humidity do you think your indoor air typically is?
I don't know, but it's very dry.
So thank you for speaking up, Kirsten. It looks like Phil put in 25. Helen put in 70% when it's raining for days. So yeah, typically your indoor air is going to be somewhere between 30 to 60% relative humidity. Optimal humidity in the wintertime is about 50%. So if we go back to, oops, let's see here. We go back to this wintertime condition, right? When the vapor naturally wants to move out of the building, and we're at about, let's say, 35 to 50% relative humidity on the inside, this vapor control membrane has a very low perm rating, right? Maybe around 1 perm. So this is preventing, again, that humidity from getting into our insulation and into our framing. Now, again, going back to that summertime condition where, let's say we had moisture saturate the insulation here, and we have summer sun baking the outside of the building, and now it's pushing that water vapor to the cold side of the wall. Once this material experiences, 80 or 90% relative humidity, it opens up to 13 perms and is not considered a vapor control material at that point, right? Because once you're above 10 perms, you're no longer a class 3 vapor retarder. It's not a vapor retarder at all. So let's look at a real life example of this, right? This was a study performed by Proclima over the course of 10 years. This is an unvented roof assembly, steep pitch, north facing, high altitude, cold climate. And, imagine, like I said, an unvented roof, there's insulation in the bays, and then they have an interior air and vapor control membrane, or excuse me, a product, I should say, or material. So there were 1, 2, 3, 4 different interior vapor control materials that they studied. And what they found is that OSB and a polyethylene sheet, these did a great job preventing water vapor from getting into the roof, but they didn't allow for inward drying, right? Because they have fixed perm ratings. This vapor variable and then smart vapor variable membranes, these have, a little bit of wetting in the winter, but then they dry. A little bit of wetting in the winter, then they dry. So they can dry over time, creating drier conditions for our roof and wall assemblies, which again reduces the likelihood of mold and rot. and makes healthier, more long-lasting assemblies. And so what I want you to imagine here is imagine that we did have a water leak in the roof, and now water has gotten in there, right? So all of these lines would go up much more. And the polyethylene sheet and the OSB would go up, and then they would not allow for inward drying. Whereas with the smart vapor variable membrane, if this line jumped up, we still have the opportunity to dry year over year. So again, we can't control all risk associated with moisture, but what we can do is set up our buildings to manage that moisture in more effective ways. Any questions on the vapor control section?
I do, sorry. Could you go back to the roof sections? Yeah, so I was wondering, so the blue line, I'm assuming that's the waterproofing layer, and then
Hmm.
then there's the like a spacer, and do you have like is that rigid insulation or something there? And then there's another layer of plywood, and then the roofing, is that the assembly?
This is more of a European assembly, and they don't use sheathing over there. So what they oftentimes will do is put this blue roofing underlayment directly over the framing. And then these little 2x create essentially a rain screen, right? It's creating a gap that air can move through.
Oh,
And then they have that layer of sheathing above to carry the
okay.
roof material.
All right, so then I have if I wanted to use, I wouldn't really be, so this is assuming that this is a fully packed cavity that has no air movement in it, in the insulation. Is that correct?
Yeah, that's correct. Hmm.
Okay. All right, thank you.
Yeah, no problem. I appreciate the questions, Kirsten, so thank you. Does anyone else have a question about the vapor control section?
I do. I have one.
Hey, Kurt.
Yeah. Hey, just a quick question. The smart membrane, does it ever get Alzheimer's? Like, it sounds technologically wonderful.
Hmm.
Um, does it deteriorate and become less smart? Like, can I really count on this thing for 50 or 100 years? What is the mechanism? And I think that's the question. Yeah.
Yeah, definitely. I know some of these products have been used in the market for about 20 years.
Mhm.
So, that's how long some of these materials have been available. Um, there have been studies on these materials, like this one here that is showing that opportunity for inward drying. And especially with these materials too, some of them are designed to take on UV light or be protected from UV light. So for example, this product here, right, it's exposed to UV, right?
Uh-huh.
And this product is designed for that, and it has a rating for UV for a certain amount of time that it can be exposed. If we go back a little further here, this product here, this one's designed for interior applications. So this one essentially doesn't have like a UV rating. So
Mhm.
if, this sits outside in the sun for 2 weeks before it gets installed, then you may have compromised the material itself. Um, but essentially, it's the advanced vapor control that you're getting inside the material that is creating that humidity dependent moisture control. So like all things, I know there's a specific manufacturer on the market that does permeance testing on every single batch of material that they produce. So there's a bit of quality assurance, quality control prior to the material leaving the factory in Europe and coming here to the US to ensure that those materials are managing humidity as they've been tested and as they're spec'd.
And just what about things like the effect of moisture and even, oxidation on them, when they're fully installed inside the assembly? How confident are we that it's just going to continue to operate as designed?
I guess what concern do you have about this going in, and I guess what's your concern if this material doesn't operate how it's designed?
Well, I guess just referring to your slides, if it stops changing its behavior based on
Hmm.
changes in humidity, and it'll go one way or the other, either become very permeable, very vapor permeable, or very not vapor permeable. It'll
Hmm.
stop like oscillating between the two modes and just get stuck in one, and then start
Hmm.
performing, poorly again. More like something not smart, right? Like a polyethylene sheet or bitchethane or, whatever. It'll just become not smart. Um,
Yeah,
and
no,
I don't
certainly.
know that
And
it will. It's just a concern that comes up because it sounds so sort of brilliant and alive. And I'm
mhm.
just wondering, will it stay that way after it bakes and, is exposed to oxygen and moisture and,
Yeah, that might be a good question for me to follow up with you on.
okay.
If you want to ping me an email and I can kind of check in with our technical team a little bit more on that. But I think, we are confident in the materials and we, know the quality assurance and quality control tests that are being done for the material.
Hmm.
Um, and they are protected because they are in the walls. Of course, they are being exposed to different insulation products. Wood framing, but it is designed for that application. So,
Yeah. Yeah.
um, yeah.
Okay, yeah, I'd love to know more. It's just kind of a devil's advocate question because we were this excited about spray foam,
Mm,
20 years
hmm.
ago, right? Like
Right.
spray all this stuff in, it'll seal every crack, it'll perform so well. And with each year that goes by, we're like, oh God, spray foam, it's awful. But there it is inside a lot of walls I spec'd it for, and especially on vented roofs. So
Right.
just
No,
wondering.
I hear you. Yeah. Well, yeah, shoot me an email and we can
Okay,
continue the conversation.
okay, thank you.
Uh-huh. All righty. Well, I think I will keep going since we're about 15 more minutes and we'll get to the end and then we'll see if we have any other questions. So again, our high performance building, right? We're talking about the robust enclosure. We're managing water, air, and vapor control for long-term durability and health. To make that building high performance, we also want to thermally control the building as well and avoid thermal bridges. So I'm sure many of you have seen this building. It's a really cool looking building. Um, it's Aqua Tower in Chicago, which was certified LEED, and they have these really great concrete balconies. And unfortunately, they decided to value engineer out this thermal break, which is a foam-based product. But essentially, this foam-based insulation would have gone in between the interior concrete slab and the exterior concrete balcony. They decided to take it out of the build to not install. So now we have a continuous layer of concrete that transitions from the interior side of the building to the exterior side. And we essentially have created a really great radiator that's heating up the earth. So um, it's probably not the most comfortable place to live. And the mechanical systems are probably working overtime to keep things at a comfortable temperature. So you can see here, this is how the continuous slab looks in terms of the effective R value and percentage of heat loss. And then we have over here on the right, that thermal break product, which is providing a high level of R value between the interior and exterior slabs and creates much less heat loss. So if we are going to use exterior continuous insulation on the outside of our building, we like to encourage folks to use something vapor open. That way, when you're heating on the inside of your building and water vapor naturally wants to move out through the walls, you have that opportunity to dry out. In masonry construction, existing masonry construction, if you do want to provide a continuous insulation on the interior side of the building, there are materials available for that that come paired with an air and vapor control material on the inside. And these are, vapor open as well. So they'll allow the building either to dry inward or outward if moisture does get into the wall assembly. And then another thing with respect to indoor air quality and thermal control is at these thermal bridges that are not thermally broken, we can actually have condensation and moisture issues because we have cold components that may be engaging with warm air and sucking the moisture out of that air onto the surface. So, this is a skylight product on the market. This is triple paned. It has a thermally broken frame. And as you can see here, in the isothermal analysis, the interior side of the frame and the glass stay nice and warm. So this means that when warm air connects with those materials, it's not going to condense moisture. And again, if we do have these thermal bridges that are buried deep in our walls and warm, humid air does reach that surface, we can have some condensation issues, and we'll certainly have some energy efficiency and comfort issues as well. So just to summarize, right, we want to make nice airtight buildings, watertight buildings that create really healthy smoke-tight homes and very comfortable homes. We want to use continuous control layers, water, air, vapor, and thermal control. Minimizing the use of plastic foam insulations can increase durability, increase our drying potential, and give us the air tightness that we want long term, again, by minimizing the use of plastic foams. Using a blower door is always a really great opportunity to really verify and see how airtight and smoke tight your building is. And then we also want to protect those control layers as well. So yeah, thank you so much everyone for your time today. Again, my name is Ian. I'm a product consultant at 475. I live in Oregon and I do travel to the Bay Area every so often. I'm actually going to be at the USGBC Green Building Conference in San Francisco on May 22nd. We'll have a booth and I will be in the Smoketight section of the conference. So if you want to come say hello and you were already planning on being there, I'd love for you to stop by. And again, what I help my clients with the most is that water, air, and vapor control. And then I support with heat recovery ventilation systems and foam-free assemblies. So yeah, thank you again so much for your time. I'm happy to answer any other questions you have regarding the presentation or regarding 475.
I have more questions if it's, but maybe someone else should go first because I obviously had some airtime. All right, if no one else wants to ask something, I'm curious still about the full cavity insulation, because right now, like if I try to do this in my projects, and my understanding is something you haven't really mentioned is the condensation point, or maybe I missed it. So what I do is so I can use pretty much anything I want on the interior. Like mostly it's been rock wool, but I mean cellulose would be great material to use. And then what I do is I have an exterior layer, and a layer of exterior insulation on the outside of the sheathing, so just to move the dew point outside of the framing, and then then I have to whatever I need to do to install whatever the roofing is on that side. And then I do need to have some kind of membrane, and that's where I always need to refer to the literature again, like it's probably one of those permeable membranes on the inside of the cavity, because I want to, if any indoor moisture gets into the insulation, I want it to be able to come back out, but it can't be totally closed off. But that's what my understanding is currently. And I did that with rock wool, and they have like a building lab where one can present them with, you know,
An assembly.
an assembly, and then they do a computer simulation similar to what you showed us with the different the graph, the zigzaggy graph that shows how much water is there during the winter and the summer in the assembly, and whether it comes out or not, and whether, so just to check that there won't be any mold.
Yeah, definitely. And I think I might be hearing what you're saying. So like I mentioned earlier, there are a lot of ways to achieve that air control strategy, right? That can be your WRB or your house wrap on the outside of the sheathing. It can be, taped butt joints of the sheathing. It can be, interior drywall, or it can be like that air control layer that we were talking about earlier. Um, so your air control layer can be in a variety of places in your project, and we can achieve really high standards of air control by honing in on one air control layer, like specifically the WRB, right? But there are some projects that are retrofits. They might be doing a full gut rehab on the inside, so our only opportunity to air seal is on the interior side of the building. That's where using that interior air control product can give us the um, uh, can give us what we want out of our air control strategy. With respect to dew point, right? And I think what you're talking about is in the Bay Area, you might add R5 exterior insulation to the outside of the wall. That puts the dew point outside of the wall sheathing, and you're not as concerned with that condensation risk, right? But there are certain assemblies like a double stud wall, um, or some retrofit assemblies with like an exterior eye joist that really benefit from that interior air and vapor control. So, to your point, is an interior vapor control membrane required to keep your wall safe if you already have continuous insulation on the outside? Not necessarily. It would be a second form of safety, right? So you've got the exterior continuous insulation on the outside, and then you also have this interior air and vapor control layer that's providing even more durability with respect to preventing moisture from getting into your wall in the first place. It can be especially critical around window openings and things like that, where you have lots of framing members, which could potentially impact the dew point. So does that help kind of answer your question?
I think I understand it now. So you're really controlling even what moisture goes into the cavity at all.
Mm-hmm.
Yeah.
Mm-hmm. And again,
Right.
it's because, if our walls get wet, right? Like if you have that, and in that interior air and vapor control membrane, it's protecting your wall from interior sources of moisture, right? You've got your WRB on the outside and your rain screen and your siding that's protecting the exterior or for the building from the exterior environment. And then that interior air and vapor control membrane is protecting your walls and assemblies from interior sources of moisture
Yeah.
as well.
Yeah. It's on, I think it's a really good, I really like the idea of it. I'm not sure about, I think, it's going to be a big push to to get people to do it because of you have all
Mm-hmm.
the penetrations there with outlets and recessed cans and whatever all the penetrations that go through the interior. So and that's why you have that sacrificial layer, right? So that would really help um
Mm-hmm.
to move all of the you shared that, yeah.
Yeah.
Yeah, I
And
get
and
that.
yeah, and just to jump in again, I support my clients in 8 states with their water, air, and vapor control strategy. So as you know, every project is different. Those connections between the roof and the wall or the wall and the floor can be different on every single project, and there can be different conditions in projects as well. So what I can help you all with is identifying how can we sequence our air control layer around the entire building to get those performance benefits that we want. And then sometimes those air control benefits also provide us additional moisture control benefits. To touch back on something else I went over in my presentation is we were talking about peel and stick WRBs, right? Peel and stick house wraps. So those products inherently make our building more air and watertight because neither water or air can move between the sheathing and that WRB because it's actually stuck to it. So we also see people achieve really high levels of water and air control by only focusing on a peel and stick product. And yeah, Kirsten, if you want to shoot me an email, I'd be happy to connect with
Yeah.
you as well. Yeah.
Maybe I'll join your meeting with Kurt because I think we're going in a similar direction. Yeah,
certainly.
and you know, the other thing, well, I guess we should just leave it at that so you can get the rest of your day. Yeah, thank you.
Yeah, yeah, no problem. I know we've got just a couple minutes left, but yeah, anyone else have a question? And if not, maybe I'll let yeah, Sydney take over and close things out.
Okay, then. Well, thank you very much, Ian. Thank you for everyone who was able to attend. And we did record this webinar today, so that'll be up on our YouTube channel most likely by the end of today if you want to review any of the information that Ian talked about. Thanks, everyone. Have a great day.
Thanks, everybody.